Okay, so let's start. I'll be handing out sort of the first homework, hopefully by Friday. I was waiting for the class to kind of stabilize. Interestingly, of the original people who had registered, almost all but 4 or 5 dropped the class, so everyone else is from kind of the wait list. Unfortunately, sort of that complicates things for us. So anyway, hopefully the class is stabilized. I'm not going to hand out any more PTEs, so we're done. Okay, so um, we're going through platforms, and I wanted to kind of go over that. And then there's another slide set I posted this morning, which is on software organization. So that would be the next topic. So last time around, we were kind of looking at this issue that how there's a variety of processors, and kind of the main thing which often in embedded systems we end up facing is that there's a choice between things which are more powerful and actually are more efficient in terms of processing in bulk. But on the other hand, they are very inefficient in terms of power management, in the sense that they consume a lot of power when they are asleep, as in they're still powered up but not doing anything, or are in one of the sleep modes that the processor provides. And also they take a lot of, they're more efficient in terms of waking up and going back to sleep. So power management, a processor is excellent in power management if it has 2 characteristics really. One is that it consumes very little when you are doing nothing. And also secondly that you can rapidly wake it up and put back to sleep. Now rapid wake up and putting back to sleep usually rules out the fact that you can power it off, as in turn the power off. The reason being that when you turn the power off, then inevitably, because of the circuit delay, circuits have capacitances and all, it takes some time for it to wake up, for clocks to stabilize, all those things. So usually what processors do is they provide various kind of sleep modes. In fact, most modern processors have many sleep modes. They go under the name of sleep, idle, dozing, all sort of things. And the deeper the sleep they are in, the less power they will consume when doing nothing. But the more time they will take to come back up, because more state is lost. So for example, they may not preserve the state of registers, maybe the memory will be, dynamic memory will be lost, maybe clocks may be turned off, all those kind of things the deeper they are in sleep. So it all boils down to how much state you have to store and how much state you have to reinitialize. Totally deepest sleep may require a complete reboot of the operating system. And before this issue was in something that paid a lot of attention to, operating systems were not really designed for rapid boot up. So if you just go back like maybe 5 to 10 years kind of time frame, our computers used to take a lot more time to boot up. But now our devices, phones and iPads and these kind of things, they come back up very rapidly. And part of the reason is that OSs have paid a lot of attention to the boot up process. To give you an example, earlier days, and perhaps on desktop still, Linux used to, whenever it would boot up, it would check the USB bus to see what are all the devices, and it would do so by some sort of a probing mechanism, and that would take a lot of time. And the problem was when you went to sleep and when you came back up, people would unplug devices or plug in new devices, so the discovery process would have to be done totally afresh. So these are little things which really kind of are coping with worst case scenarios, but would complicate stuff. So this slide was kind of giving the example that how 2 processors, these are older processors, but the same point being made, which is when it came to bulk processing, like doing things like FFT or CRC check and these kind of things, the little processor took a lot of time, and needless to say, but also a lot of energy, and which is what we are showing out here. And for doing the same task, the big processor, because it has the advantage of 32-bit, it has the advantage of better architecture, perhaps data cache, those kind of things, it kind of has a couple of order of magnitude kind of advantage. And same thing with other stuff. On the other hand, when it came to sleep mode power and boot up time and all, you're comparing things like tens of milliseconds for the big processor to microseconds, or nowadays, I mean, you can boot things up and all in a few microseconds with small processors and consume maybe a tenth of a microwatt, whereas big processors still are into milliwatt and kind of ranges. So that's one thing. The other thing that happens is that we often use specialized processors, or the name which is used is domain-specific processors. Processors whose instruction sets have characteristics catering to some specific domain. Most common one is for signal processing, and particularly in embedded systems because there are usually sensors to be processed and all. They're architecturally similar to kind of at some level they are just general processors, but they do have additional capabilities optimized for numeric tasks. So for example, you will find that in signal processing, a very common operation is multiply accumulate. So like kind of doing things, you have a variable in which you keep adding product of two other numbers, and you kind of keep doing it. It's a very common operation in signal processing, and therefore oftentimes these processors have a single multiply accumulate type instruction, or they may have an instruction for doing FFT or things like that. Things which are, or FFT actually turns out to be something where instead of when you're addressing memory, instead of addressing memory in a linear fashion, kind of striding along addresses 1, 2, 3 like that, you kind of jump around in a butterfly fashion. So they have these special addressing modes, things like that. So oftentimes you'll find that processors or so-called system on chips come with a tiny DSP on it, and a good example is if you have an Android phone, you're likely using Qualcomm Snapdragon chip, and it has a hexagon DSP, and which actually a few months ago they opened it up for developers to kind of use. Previously, it used to be kind of hidden. TI OMAP chip, same story. So which is a chip used in BeagleBone, for example. So there are plenty of examples of main processor, which may be a general processor like ARM, coupled with a DSP to go with it. And then there are, of course, specialized DSP also, so processors as well. Now, at the end of it, the goal of all of this stuff boils down to the following, that at least in the more energy constrained type systems, what we want is this concept of energy proportionality. And the idea is that if the workload on the system varies, and you want the energy taken to, or the power, the energy taken by the platform to scale with the work you are asking to do. So if it's doing nothing, ideally it should consume nothing. And if it is operating at full workload, at its peak performance, then that is when the peak energy should be consumed. So for example, if you look at like even a device like a mobile phone, even when it is in the idle mode, okay, so what happens? Most of the time it's idle, the screen is static, then your clock updates, so some action happens. Then when the user tries to swipe open and all, more action is happening. So even in the simplest of the modes, there are kind of all these things where different amount of stuff is happening. And increasingly they have things like many phones have now, even in the passive mode, they are listening for your voice, and so they get activated. So like Google or Apple Siri, both of them have some similar things, or face-based authentication mechanisms, these kind of things. So the main point is that workload varies, and you want the processing capability and particularly the energy consumed by the processor to kind of scale in the same fashion. So ideally what you're looking for is kind of a situation where as the performance goes up, energy per unit time, namely power, kind of scales with it. Now, a limited amount of that you can accomplish within a single processor. Most modern processors allow you to change the voltage of the processor and along with it the frequency of the processor. And therefore you can scale the performance. So kind of in my 202B, I kind of go in depth into it, but sort of the way electronics works is by changing voltage and frequency together, you can achieve kind of like, you can have your processor kind of straddle some sort of a curve like this, okay, where the higher the performance you need, the more energy you need per unit work. Okay, so it's not linear. It kind of efficiency begins to go down as you are going higher up, but nevertheless it lets you straddle some region of the space. But the problem is that this alone is kind of only part of the story, because as we saw, little processors versus big processors, specialized instruction sets versus general instruction sets, they will all have their own impact as well. So what has begun to happen is that increasingly you will see, as I mentioned, that you will see multiple processors get combined together. So one concept is that I take two processors of the same type, but two different implementation. But by the same type, I mean they have the same instruction set, but different architecture, different implementations. Are like they may have different amount of cache. They may have other. They may have one may have deeper pipelining the other, or they may be able to handle multiple instructions at the same time. These kind of capabilities. So you often see kind of two cores of the same instruction set put together in a very tight coupling. And ARM calls this big dot little. So big processor, little processor paired together. And kind of the idea is that through some intelligent software mechanisms, you can switch between one or the other, or use both as the case may be. So when you are when the system is in a mode where it just has to be vigilant, looking out for events, doing little stuff and all, perhaps you shut the big core, keep the little core active, and when something happens, you realize it's interesting, needs a lot of processing, kind of you activate the big core. This is also kind of, you find this kind of structure also in Samsung's chips. So Samsung uses these chips called Exynos, which are found in many of their phones, and they actually have clusters like these. Now, this takes us, this lets us basically have a wider range over which I can change performance and power. Then additional stuff is then we begin to use the specialized cores. So these are more loosely coupled. These could be microcontrollers. These could be things which are dramatically enough different in capability that you may not be able to run them under the same operating system. So they may have similar instruction set architecture, or they may be DSPs and things like that. So to give you an example, many chips, including Snapdragon, which I had mentioned earlier, they have a very tiny version of ARM processor, the same one which you find in your embed devices, the Cortex series. So while in theory the instruction set is the same as the big guys, you can take code and kind of run them in both directions, but these are so resource starved, kilobytes of memory and those kind of things, that you really have no hope of them running under the same operating system management. You cannot offer the same software environment, and so these need to be more loosely coupled. And there are plenty of examples of these. So and they usually get used for the more specialized kind of parts of the system, or perhaps kind of this is the only thing which may be active when you are in a really deep sleep mode. So like iPhones have this M7 processor, which is really a Cortex M3 chip, and that is how it kind of keeps track of the accelerometer and some of the other inertial sensors which need to be active kind of all the time. And other devices have same thing, like Snapdragons also have actually several Cortex M3s inside the chip, which they do not expose to the programmer, but Qualcomm uses them for sensor processing and all. Let's see. So what other examples I can give of this? So DSPs is other examples. If I were to characterize Snapdragon in this space, so Snapdragon does not have big dot little. It only has a bunch of big processors, and then it has a bunch of loosely coupled processors, DSP and Cortex M3. If I look at Samsung's chips, they have gone for multiple big dot little processors. If I look at Apple's, and I'm ignoring that almost every processor on the mobile space also has a GPU, which you can think of as a specialized, loosely coupled specialized processor. If I look at Apple, it again is more like Qualcomm's Snapdragon, namely multiple big cores and a loosely coupled kind of a little core, and then of course the GPU. If you look at more mainstream processors which are in the non-mobile type embedded space, they usually don't have the GPU, but otherwise they're following basically the same trajectory. It's just that they are a thinner, lower margin market, so you sort of hear less about those processors, but they are actually higher in volume. Any questions, comments on this thing? So,
is the small core and the big processor are the same thing for the same purposes, or like different things?
So big dot little, the two processors are architecturally from software perspective the same. They're tightly coupled. By tightly coupled, I mean they share memory and all. Okay, so they run under the control of the same operating system. So you will have Linux running, and basically some threads or processes could be put on the big, some on the little one. It may decide to put big core into sleep or little core into sleep, kind of does that management. But for all practical purposes, it's no different than your multi-core processors that you find in your laptops and stuff like that. The difference being that in normal cases, these are homogeneous cores, as in identical in capabilities, whereas here what you have is these are cores which have same instruction set. They are tightly coupled in the sense they share the memory space and all, but they are heterogeneous in terms of the performance. Okay, so they just kind of activate them differently. Where the stuff out here may have the same instruction set architecture or may not, depending upon, but it's loosely coupled, as in it will come with its own little memory and all, and usually there is significant difference in its resource capabilities that you will likely not be able to run them under the control of the same OS. This will kind of be a separate little thing. Right? So, upshot of all of this is through these mechanisms, kind of you essentially seek to straddle this entire space of performance power that you kind of want, and again, kind of specific details depend upon systems and all, but that's kind of the goal out here. So going back to our example, if you can imagine that smartphone sitting on its idle screen, most of the time the small processor is running, but whenever there's some action happens, user swiping or whatnot, the big processor is immediately activated, and that's what it kind of handles. So this is what, as I said, ARM calls as big dot little. And usually the combination that you would see is a combination of the A7 type processors and A15 type processors. And just to show you, so again, you can run Linux on both of them or whatever, a big operating system on both of them if you have sufficient memory and all, same instruction set and all. But you would see things like this guy has in-order processing of instructions and a pipeline length of 8 to 10 stages. So it's a simpler execution unit inside the processor. Here it's out-of-order processor. Anyone knows what out-of-order processor means? Right. So let's say you have an assembly program. Not in order means that the instructions are executed in the same order. Okay. Now the thing is, if oftentimes the instruction ordering may be over constrained in the sense that I could run a subsequent instruction before or together with a previous instruction, because if there is no data dependency among them. And so if you have adequate hardware support, you can kind of do this kind of processing in an out-of-order sequence if the hardware thinks that that would lead to a more efficient usage, for example. So this guy obviously has a more complicated thing, a deeper pipeline. And then additionally, for example, each execution unit has single queue and 2 instructions can be sent. In this case, multi-stage queue and 3 instructions can be processed per clock cycle. So just generally speaking, it's an architecturally more complicated processor. A lot of these things are really optimized for speed, performance, and they'll likely do well on even in terms of power for complicated things. But the penalty would be all this hardware, when not used or when just idling, is going to consume a lot more power. So A7 cores can handle the easy stuff. A15 cores will kind of handle the more complicated stuff. That's kind of the example. And as I mentioned, Samsung Exynos is kind of like that. So what it does is it pairs, I think it has 4 pairs or 8 pairs of these, 4 pairs of big dot little, 4 pairs of big dot little. Now, since these are relatively new technologies, so the operating system's ability to fully utilize these capabilities is still not fully mature. So at least earlier, when these things had come out, there were limits. Like you could switch to all, you can have all little or all big, or within a cluster you can have a big or a big one or the little one, but not both. So there were limits to the different permutations that the operating system, permutations of active and idle processors, which the operating system could actually leverage. But these things are kind of rapidly kind of improving. In the non-mobile space, big dot little still hasn't penetrated, but it's just a matter of time. With a few years lag, you would see that. And in fact, all these companies, particularly Qualcomm, is putting Snapdragon for kind of the more deeply embedded market as well. Really, the only difference is that you don't need the GPU. Everything else kind of follows in that space. So one of the things that to make use of this big dot little is that you may need to migrate tasks. So what's happening is, let's say there is so uh, early versions, the earlier model of support was that within a pair of big dot little, I can have one or the other active, not both. So in such a case, if workload increases, I have to migrate tasks which were running in the little core, let's say, to the big core, or vice versa. And so firstly, that itself means that my instruction set has to be absolutely the same. I should be able to copy registers from one core to the other and kind of just start from wherever I was. You would see that sort of migrating tasks like this kind of does cost, right? Because you have to sort of shift some state from one processor to another. That would be one issue. The other thing is each one of these will have their own caches. And the moment you move, the cache is no longer valid, and therefore there is further hit in the performance. So it can add up to a reasonable thing. So it's this thing is not something you can do willy-nilly. You have to kind of decide that there is a reasonable likelihood that you're going to stay put in this new choice that you have, so that this transition cost is amortized. This is still much better than kind of booting up an OS and all, but nevertheless, when you're looking at these processors which are nowadays operating at like close to a couple of gigahertz, even in our mobile phones, this is significant. Other things that need to be done is interrupts which were being handled by one processor now need one core now needs to be redirected to the other one. So the hardware has to also kind of cooperate in this process, and kind of there's an interrupt switch, if you may. And likewise, cache states need to be done. So the way they do it is, uh, even the sleeping processor kind of keeps track of what is happening in the active processor, so that when we restart, you're not really starting from a totally cold hardware, basically. Okay, there's some initial state which sort of helps you there. So a lot of interesting stuff happening, and but at the heart of it is this task migration. Now, if on the other hand I had the ability to keep both of them up and running, then perhaps task migration needs would be somewhat mitigated in that regard. So yeah, this is just a plot of that. The other, so this is a task migration based approach, but then more sophisticated, if your scheduler allows that, is that now you can decide other different permutations beginning to happen. So for example, it could be that I can, so one simplest model is that I switch from all little to all big. More complicated model is that within each cluster, I can make a choice whether big or little is active. And the final one is totally fluid. Okay, I can decide whatever subset I need at any given point in time. It can range from one little to all the four bigs, or and anything in between. And it really just boils down to the ability to schedule these things. And I think so what's happening is, over time, since big dot little was kind of a new edition, widely available only basically over the past year and a half or so. So the OSs are still kind of catching up in that regard. But it does lead, the big advantage really, I mean, this is being driven by power, overall power savings that you're kind of seeing with these kind of games being placed. So there are specific operating system projects very active, which is how this stuff is going. There's one called Linaro. These are specifically aiming at how to leverage these newer advances in terms of cores which have heterogeneous capabilities, or even loosely coupled core. There is, for example, so leveraging those DSPs and stuff like that. So there's some work some of the groups have been doing, not yet sort of on the commercial side, where trying to give the application developer same programming abstraction, same set of APIs, whether you are writing it for the ARM processor or whether you're writing for the DSP, and then the underlying runtime kind of makes the magic happens and puts things in the right place. I mentioned DSP with Snapdragon, so this is an example out there where so this is kind of one of the Snapdragon chips, and what you see is, so Snapdragon calls this ARM processor to be the crate CPU, so these are a bunch of big cores with a shared L2 cache. They have a GPU, but additionally they have this hexagon DSP, and actually they also have some other Cortex M3 type stuff which is not hidden in these things, but this is something which is now also user programmable. So now you can imagine that if I'm processing, doing some audio processing or some signal processing type stuff, I can actually take that function and farm it out to the DSP, and perhaps then this guy can go to sleep, or it could simply be an additional computing resource, because for certain kind of computation, this is more efficient in doing it also. So a lot more complicated, and I think our ability to program these kind of architectures is still sort of catching up. Apple, as I mentioned, is more of an example of a loosely coupled thing. So it is in the same vein as this, except that Apple has not opened up any processor on this side. So you cannot program their M7, but they have an API through which you access its capabilities, and also it's sort of exposed, but not available for users to use. TI OMAP. It's a complicated chip, but again, without going into kind of walking you through this, it has a big processor, it has a microcontroller type thing, so Cortex thing, and it has a DSP, and you can program all of these things. And TI historically has made chips which are the most open, in the sense you know everything about the chip to do it. The flip side is no one uses them, so they have killed this product line. So actually the chips being used in BeagleBones and all, really, I mean, that group in TI is shut down, so there's no future there. And by the way, Raspberry Pi uses Broadcom's chips. Broadcom's chips have historically been closed, in the sense you cannot download their data sheet and all. So that's one of the ding against Raspberry Pi, which is really, if you want to do low-level stuff, you really can't, because there's no information. And I think Broadcom is going through the same phase of moving outside the mobile market. So Qualcomm is the big mobile SoC company. Who do you think is the other one? MediaTek, exactly. MediaTek actually is bigger than Qualcomm in volume and lower in dollar revenue. Okay, so it's a Taiwanese company. I guess we haven't heard of it that much in this country yet, but they actually have the biggest market on the low end side, so they just dominate on the volume side of things. So mobile, I mean, it used to be that. So if you look at the embedded space, large number of processors are kind of the microcontroller things, stuff going into your cars and all, and then the smartphone one. But what's happening is these markets are kind of melding, and as basically the embedded processors for non-smartphone is basically the low end of the smartphone embedded processor. So the very same companies, I mean, once all the 6-7 billion of us have smartphones, then Qualcomm's and all, for them to grow, they basically want to go to the traditional embedded market, and that's kind of the game which is being played at this stage. I mentioned some of the academic work on programming abstraction, so that you can give programmer the illusion that the same kind of APIs and all from ARM and DSP or whatever loosely coupled processor. So the group I mentioned was this group at Rice University, and so they have this operating system, open source. You can download and run it on OMAP. So I think it will run it on BeagleBones for heterogeneous processors. So they basically try to give the illusion that state is being tracked across otherwise loosely coupled processors. So the operating system takes the burden of moving things around and offering kind of same kind of APIs and all on both sides. So generally speaking, sort of making complicated hardware is hard, but nevertheless the easier part. The harder part is making programmers be able to efficiently use it and write code which is correct and will work correctly, because all this complexity kind of taxes our ability to write software for it, and that's kind of the phase that we are going through right now. So that was kind of a quick overview of what's happening on the processor side. I think this some of the newer processors that are coming out and all, I think these are great topics for additional kind of investigation on your own as well. I mean, this is obviously kind of a very detailed topic. The processors we are using through those two boards and all, they kind of represent not this kind of a cutting edge stuff. If you want to use some of these architectural features, your phones are probably the best platform that you can have. Let's go into communication and I/O interfaces. So that's kind of the other critical part of embedded systems. And again, kind of main thing out here is, since we interact with the physical world. So there is a whole ecosystem of sensors and actuators and other things that you have to interact with, and therefore there are a whole bunch of interfaces that have emerged, both wired and wireless. And these are things that you normally don't hear about in general purpose computing, but they are around. So like for example, CAN. Anyone knows what CAN bus is? Area network. So where is it used? Cars. Yeah. So it's very dominant in cars. I2C. This is something actually you do find inside your laptops and all. It's just that it's totally hidden away. This is how some of the power battery and power management, particularly batteries, usually offer an I2C interface, for example. Okay, so some of the stuff on your general purpose computers also use I2C. It's a serial bus with multiple master capabilities. SPI, serial peripheral interface, is perhaps the simplest of the buses. Just a pair of devices. UART is our good old serial stuff. Most UARTs can be operated in two modes, asynchronous and synchronous. And you'll see that in your embed also. So asynchronous refers to the fact that the two sides do not have their clocks a priori synchronized. Clock frequencies are not synchronized, frequencies and phases. And so whenever a packet goes out, before the packet are some bits which help the receiver learn the rate at which the sender is sending stuff and where the bit boundaries are. In the synchronous mode, things are kept synchronous, and therefore data can be pumped much more rapidly at a higher rate. So you'll typically see that in asynchronous mode, UARTs may go up to maybe 100, 200 kilobit per second, but in the synchronous mode, you can pump up to maybe a few megabit per second. Okay, so that's kind of the performance benefit you get. And then USB and kind of USB 2.0, 3.0, all those things. And then, so these are common ones. Excuse me. Some of the other higher performance stuff that we are used to in our general purpose computing, like things like the FireWire stuff or the other higher speed serial links that have emerged, which kind of are too power hungry to find their way out there. Communication with other embedded systems is usually in the wired domain is the good old Ethernet. But then more importantly now is the wireless interfaces that are emerging. And there are a whole bunch of them which are catering to the embedded market. And really the difference is whether they're targeting short range, mid range, long range kind of communication. So let's look at CAN bus just as an example of this thing. It's a pretty old, well-established thing. And in fact, it will probably begin to disappear because its main market, cars, are moving upstream in terms of their bandwidth requirements and all. As we begin to move towards self-driving cars and all, there's a lot more higher rate sensors and all that have begun to emerge. But the good old CAN bus, just to kind of give you an example of what's happening is, so it's a serial link, 250 kilobaud to 1 megabaud kind of thing. And what it does is it's a priority-based bus. So this is what happens out here. That I have multiple nodes. It's a serial bus, so there's just two wires. In this bus, serial bus. Transmitter. All nodes who wish to transmit, they kind of send out a signal on a common line, and they also monitor that line. And what they do is they start out by sending, if they wish to send a message, they are going to start by sending out initial part, which is the priority. So what's happening is that these are two nodes, and they're going to start by sending their priority bits. And the idea is that each sender is supposed to have a unique priority. So at some stage, so if you're sending out the bits and you're also monitoring the wire, at some stage you will encounter the first bit at which the different priorities of currently active senders mismatch. So let's say I have one guy whose priority is 1100 and the other guy whose priority is 1110. So both of them will send out one, match, no problems. So I'm hearing what I'm receiving. Next round, both send out one. Again, both of them hear one, no problem. Third round, one will send out one will send out zero. And the way the electronics are designed is zero dominates. So both of them will now hear zero. And so the person who's sending out one will say, hey, I lost because I'm hearing something different than what I sent out, and it kind of drops out. And this process continues, and at the end of it, there will be one person standing, and then it transmits. So that's kind of the concept. So there's a notion of priority over the shared medium, and so this kind of a bitwise arbitration that takes place. And around that, on top of it, now you can make higher level scheduling algorithms and also, like for example, by appropriate manipulation of priority, you can then arrange for certain type of traffic to get priority. You can begin to control the delay that they are going to take over the network. All those kind of things begin to happen. Now, the reason I said CAN bus is on its way out is, like I said, with the newer developments in cars, we have sensors, cameras, all these kind of things at a much higher bandwidth. So there is a newer standard which is soon to emerge, which is aiming for a gigabit per second kind of thing. So suddenly from 1 meg to 1 gig. Serial line, it's still serial because in cars, one of the big issue is the amount of weight that cabling adds. So you don't want very complicated multiple wires and all. So it's still serial, but very high speed serial, and that's expected to kind of take over. Wireless technology. So I mentioned that a lot of embedded systems are going towards that. So probably sort of the most action has been on the short range side of things. So the several that you would hear for a bit are, so there is something called IEEE 802.15.4 or so-called ZigBee. And this is really catering to really kind of the hardcore embedded market. You're not going to find it in elsewhere. Home automation, sensor networks, probably, I'm sure some of you at least would have seen these network connected LED light bulbs that a bunch of companies are selling, Philips Hue and LifeX and things like that. And these are all using ZigBee. Okay, so usually the bulbs have a ZigBee radio that talk to a little hub, and that hub then connects through Wi-Fi or Ethernet to kind of your home network. So a lot of products that are being sold in the consumer arena at this stage do have ZigBee. There's in home automation thing, another big penetrator has been something called Z-Wave, which is actually a single company's proprietary protocol, but it penetrated quite a bit, and both Z-Wave and ZigBee have the following model, that they are what are called as ad hoc networks. Anyone knows what that is? You don't need a server. No, not quite. No. Right. So two good points. So two characteristics as a consequence of this. Number one, I don't need to talk directly to a access point or a base station. I could be multiple hops away from it. Okay. So that's one thing, and which is very important in buildings and all, because otherwise you have a significant coverage issue that I have to have a base station so that every point is under the coverage of some base station, and that's very hard to achieve. So that's so what a consequence in these networks is that I can be multiple hops away and still talk to the gateway. And the other one is I can exchange information directly with my peers without having to go through the access point. So for example, dominantly with Wi-Fi, the mode when, like, if my laptop were to send something to your laptop, it will go through the access point. Okay, there are things like Wi-Fi Direct which have begun to kind of loosen that, but normally kind of the idea is we both hook up to a common access point and then kind of communicate through that. So ad hoc basically means these two things. Number one, the ability to communicate peer-to-peer without involving any sort of a base station. And the other is being able to be away more than one hop from the base station. And both of these things have significant, so the latter has advantage that coverage issue. The former has advantage that I actually potentially have a better use of my wireless channel and kind of can get more out of the network as well. So both Z-Wave and ZigBee provide those kind of capabilities. Difference being this is open, whereas this is licensed. And I think over time, I suspect it will pretty much dominate. But right now, home automation products, like if you were to buy light switches and stuff like that, they are still Z-Wave for the most part, or some other proprietary protocol. And ZigBee's penetration has been more in the lighting market. So lighting is one place, also the radios and smart meters. So if you're living in a home with a smart meter, and sometimes utilities let those smart meters talk to a display at your home, they are quite likely going to be a ZigBee radio. So, and then also smart meters talking to a radio on the nearby electric pole to send the data out, they are usually also ZigBee. So ZigBee has penetrated some of these markets, and I think it's a matter of time that it would be the dominant. Bluetooth is the third one, and Bluetooth kind of started out with what's called as personal area networks, and all of these technologies, I mean, particularly this and this, have some overlapping regions. So, like for example, Bluetooth also has an ad hoc mode, which is rarely used. It's called ScatterNet and PicoNet, right? Yeah. So they have these other modes also, but the dominant case of Bluetooth is your device talks to your phone. Okay, not device talking to device directly, but there's kind of a master, and then there are a bunch of slaves, and they kind of talk to it. Bluetooth started out as kind of a pretty heavyweight protocol. It would take the two devices had to be explicitly paired, and then every time they needed, before they could communicate, they needed to kind of associate with each other. So it would take a lot of time to set things up. One of the big things which happened in Bluetooth over the past 2-3 years is so-called Bluetooth LE, or low energy, or Bluetooth Smart, which basically created a special mode which is catering to sensor type devices. Devices which need to talk sporadically at low rate but need ultra low power. And so you want them to be able to sleep for long times, wake up, and then without a lot of overhead, send a message out. So Bluetooth LE is kind of a big change. So a lot of our wearable sensors and all kind of end up using that. We'll go into more detail in Zigbee and this in a later lecture. Wireless HART is what is used quite a bit in factories now. So this is a protocol, again, ad hoc network and all, designed for sensors and all in like factories or petroleum refineries and all kind of talk to each other. Big penetration there. Little bit like this, but it has some very significant higher performance capabilities and all. Very tight time synchronization, bounded latency, so you can guarantee that packet from this node to another node will reach in a certain amount of time. So this is kind of the industrial strength stuff, and is basically being subsumed by the Bluetooth low energy. But this was again a proprietary protocol which became very popular, and even now, like a lot of these health related sensors that you find, heart rate sensors or things with if you go to the gym, the straps that talk to the gym machine and all, they're quite likely still ANT. And it is more efficient than Bluetooth LE, but you don't find ANT on phones, but Bluetooth LE is on all the phones, so it's just a market penetration sort of thing. Interestingly, though, that ANT capabilities have been available on many chips used in the phones. So any of you recall when early days of so Nike had this shoe insert which would work with the iPhone and would kind of act as a pedometer thing. So they were selling it for a while with Apple, and the reason was iPhone actually had an ANT chip. It's just that it was never made visible to the programmers. Moreover, as I understand, Broadcom's chips, which are used in the phones very widely, had both Bluetooth LE and ANT all the time, and it's just that they would activate it one part or the other depending upon the customer. So the radios were similar enough and all that they're actually all present in the chips. It's just not being necessarily activated. Okay, so that's the low range stuff. Mid range is pretty much dominated by 802.11. Okay, by mid range I mean in a single hop you want to go distances of tens of meters to perhaps a small number of 100 meters. 802.11 is the only one. A lot of attempts have been happening in 802.11 to create lower power versions of 802.11. Didn't quite kind of work out. You have Wi-Fi Direct, which is for peer-to-peer thing. A very common mode, but still it is being used. So a very common mode you would see 802.11 being used before this Wi-Fi Direct came up, that the sensors would act as an access point. Okay, so what will happen is you'll buy a sensor, and then the sensor would have the capability of acting as an access point, and then your phone will associate with it. And this is how they were kind of kludging their kind of way around this thing, because your phone cannot be not necessarily be a Wi-Fi access point, so they would kind of invert these things. So you'll find it in quite a places. 802.11 sensors are there, but they basically go through this mode where they can act as an access point so that you can talk to them. And one very common practice I see nowadays is that during setup mode, they will act as an access point. You talk to them, and then you pass to them configuration information, and then they switch, and then they hook up to the 802.11 network in your home. So you kind of go through this two-step phase to set things up, because otherwise you get this device and it doesn't know anything about your home network, it doesn't know how to connect to it, so it goes through this kind of a two-step process. So an example of the first one, where sensor acts as an access point and that's the way it remains, is some of the sensors being sold for hooking up to your car, OBD2 sensors which hook up to the port in your car. They many of them are Bluetooth, but some of the Wi-Fi ones basically become an access point. Sensors which are targeting home, like Wi-Fi based weather stations, security systems, these kind of things, they usually go through this model where during a setup phase, they act as an access point. You hook up to them through your phone, you give it all the configuration parameters, then they restart, and now they connect to your home network. So that's kind of the idea. And then finally, wide area networks. Basically, pretty much the only solution is, of course, to use cellular systems. What you see is that companies which are in this market, they create different type of pricing models and all. So whenever we get data plans for our phones, we get a per device data plan. Now imagine if you're a company running sensors all over your network, an electric utility which has sensors all over, and you have like a few 100,000 devices which are all on the cellular network. You're not going to have per device cellular plans and all. Okay, it's just a non-starter. So in this market, what has happened is that there are these companies which specialize in what is called as M2M, machine-to-machine networking. And what they do is they essentially have they buy bulk bandwidth from AT&T or Verizon and all, and then they charge you. They create these plans where you can have a large number of devices, and they kind of price you in in some different model basically, as opposed to kind of going through provisioning each and every device separately. So same type of radios and all, you'll find an embedded version of 3G or LTE that you can buy. These boards, you can insert, have them part of your embedded system. Satellite networks is another capability. It's used a lot more by scientists and all who are deploying stuff in really remote areas. And then finally, a lot of proprietary point-to-point microwave links. Sometimes people use Wi-Fi with highly directional antennas. So you can find Wi-Fi radios which can go to 50 miles or 100 miles. You can find Zigbee radios which also can go to 50 to 100 miles, but they have very high power amplifiers and very highly directional antennas, and that's how they work. So a lot of stuff on the wide area side which is happening, but most action, like I said, has really been, normally when we talk about embedded wireless, it's really this space where a lot of action is happening. Okay. So plenty of radio choices, and what again it boils down to is that you have to sort of find the right one. Just like for processors, we saw that we can combine a big processor and a little processor. It's the same thing with radios. Oftentimes you would see two radios being used, one which is called a wake-up radio. So the idea is that if I were to use, let's say, a radio like Wi-Fi all the time, then it's very power hungry. It takes, even when asleep, it takes a lot of time. When it needs to connect, it takes a lot of time to connect. So it has all the characteristics of a big processor. But then I could perhaps use one of these, like a Bluetooth LE, or there are even companies which sell so-called wake-up radios. And the idea is that your system can go to sleep, and then I need to wake the other node up. So there is a tiny little radio on that other one which is just listening for a hello message, and you kind of send that out, and this guy then wakes up, and then both switch to kind of a higher capability radio. So just the same analogies that we, things that we talked about, big dot little, kind of there is a big dot little counterpart in radio also, where you mix and match 802.11 with one of these, or perhaps even the specialized wake-up radios. Power subsystem. So actually, let's take a 5-minute break at this stage. At 10:50 points, so just. I have not used the offline, so I really cannot. It's relatively new, so I have not used it. Yeah. Yeah, I can see if anyone in my lab has tried it, but I know we have. I'm trying to recollect which student. There was one student who had set up a tool chain locally in last year's course, but I don't know how he had done it. So okay, yeah, offline does offer you some advantages, obviously. Yeah. Yeah. I'm not handing out any more PDs. Possible. No.
Can I at least like keep coming, like just to check it out?
Yeah, you can. Yeah, sure.
And no possibility.
No, I'm not going to hand out any. Okay. Because I open a can of worms. So there are plenty of students, then I'll have to open a can of worms. So I'm not going to hand out.
Okay.
Okay. Hey. Under what scenario would that make sense?
Let's say I'm just collecting data on the sensor and sending that to cloud, just to use some complex algorithms, and to use see that data and to analyze it, I can use maybe a mobile or a gateway
To see the data, I can see, but why would you call it a gateway?
It's not actually a gateway. It's just
Yeah.
it's just a
I mean, is this the visualization platform? Sure. Yeah, I mean, sensors can certainly talk directly. But I guess if they're using Wi-Fi, there's always a gateway. Okay. If they're using cellular, that's the only time. I guess even there technically there's a gateway.
there is a gateway. But I mean, is that okay for the project environment, or it has to be the
No,
whole
that's
sensor?
fine. That's fine. Yeah.
And,
But
and
so what are you thinking?
I don't have a very concrete idea, but I'm just trying to figure out what are my options really, which device I can use. And
Yeah,
also,
I'll be putting out some topics.
because we have to submit the
No, I'm going to push it back. This took time to stabilize. Okay.
and let's say my project involves using some complex algorithms like machine learning or voice analysis. So let's say that algorithm is in cloud. So will the part of the project also involve writing the algorithm?
I guess so. Yeah.
Because
But for machine learning and all, there's plenty of support out there. I don't know what kind of stuff you're thinking, but there are plenty of good machine learning toolkits and all that you can use to learn a model, and then you just run it as a piece of code out in the cloud, and there are
but can we
plenty of.
use that? Can we use that? Because I don't know whether that matches with the academic integrity stuff.
You can use anything out there as a software tool.
Because technically writing that complex stuff is not actually embedded. I mean, it's there.
Right,
So I
right,
don't know
right,
whether
right.
I should do that or whether I can assume that
Okay.
this can be done.
I mean, you
Just
cannot.
use immediate
I mean, the project has to be sort of a complete project. So if you
Oh.
don't do the cloud part, it won't make a lot of sense, right? I mean, but you can. I mean, look, there are plenty of machine learning toolkits. You can learn a model. Again, I don't know the specifics of the project, but I mean, you can train a model and then run it on a virtual machine using Heroku or one of these plenty of sort of websites which offer you free cycles.
Also, has it the project has to be achieving something for embedded stuff, or it can be more on the software side for embedded, like let's say maybe a hypervisor for a new platform or something like that.
Like I said, there could be projects which are application oriented and projects which are creating something foundational that a whole bunch of embedded systems designers can use. So I could, yeah, I could see that there may be something around hypervisor and all, which could be a general tool. Okay, sure. Hmm? You know, I think anything once you start hitting 3, usually I've noticed things don't work very well. 2 is the best. There's way too many personality issues and all which start coming in. Okay, so let's pick up this thread. The next part of an embedded system that so we looked at processing, we looked at communication. Power is the power subsystem is kind of a third very critical one, and essentially there are a bunch of different ways embedded systems acquire the power that they use. They could be plugged into the electric grid. One of the interesting technologies to emerge now is wireless power delivery. So in this realm offer things like where you actively they either there is an entity which is actively delivering wireless power to them through radio waves, or they are making use of radio waves which are just around us. Other form of environmental energy harvesting, so sun, wind, stuff like that. You would have some sort of energy storage device usually, either which is getting energy from one of these previous sources, or in some cases it's just a non-rechargeable battery which you replace. Common to all of these is that you would have some energy supply, and then the rest of your embedded system would need it in the right voltage, and so on and so forth. So a generic power supply system for an embedded system has kind of these key components. So there is some sort of an entity through which energy comes in, electric grid or energy harvester. This may not be there if you have a replaceable battery type embedded system. You will have typically some energy storage. Again, there are some systems where there may not be any storage, like for example, they only operate when there is sunlight. So there's a panel and feeding. There would be some sort of a management entity. Increasingly, this is just some software which kind of manages kind of essentially these two other entities and arranges power to be delivered to what is called as a DC to DC regulator. This DC to DC regulator, its job is to make sure that the voltage seen on this side and other characteristics of a power supply are of the adequate quality. So voltage is certainly one, but there are other things like maybe voltage has to be within some band, it shouldn't have noise, all those kind of desirable characteristics, should have adequate current capability, all those kind of things have to be managed in this process. So a little bit of next two slides of a bit of a circuit just to illustrate the point. You'll see very commonly two types of regulators are used in embedded systems, and just want to throw them out just to give you a flavor of why they get used. So a straightforward type of regulator is what is called as a linear regulator, and it's basically an analog circuit which main concept out here. So main concept of any regulator going back out here is the following. I'm getting some sort of a voltage out here, and it is of poor quality, and I need to give out a voltage of a good quality. So I'll continually measure the error between the two and then change something in my circuit so that I maintain this. It's a little control algorithm, a control loop. Linear regulator does so by making use of an amplifier. So it's basically measuring an error with respect to what I want, and then this error amplifier changes the resistance out here so that the voltage which is going out to the load is controlled. Okay. So the voltage seen out here is the ratio between the resistance of this and the resistance of this, and the rest of it is this control circuitry. So I basically have a control algorithm implemented in this. So this, again, just to recap, voltage out here is, if you recall your, must have seen in some physics courses or not, but this guy has a resistance which is being controlled by this. This resistance divided by the total resistance gives me the voltage out here. By controlling this resistance, therefore I can control this voltage, and I control this guy's resistance based upon this error amplifier. That's the main concept. The main problem with these things is they are grossly inefficient. In fact, their efficiencies could be very, very low, which basically means that I'm wasting a lot of energy. In fact, I'm wasting a lot of energy even when, as long as I'm powered up. Okay, so this kind of, these linear regulators are very simple to implement, but they tend to be very inefficient. So what you would see usually used in embedded systems are so-called switching mode power supply. And they kind of achieve the same thing, except the control now goes into software effectively, or some sort of a software thing. And the basic idea out here is now I have a voltage out here, and the voltage waveform I give to my load is a sampled version of it. So imagine I have this battery sitting out here, which is putting out a voltage of 5 volt. And let's say through this switch, what I do is half the time this switch is on, half the time this switch is off. So the waveform out here would now look like a square wave, which is 5 volt for half the time, and which is disconnected for the remaining half. And then I smooth it out through the circuitry. So effectively, I'll get 2.5 volt. So the ratio of time, fraction of time this guy is on, controls what voltage is being seen out here. Again, those of you who are EE would have seen this stuff. Main point is that I have this usually a little processor, which is sitting out here, monitoring the voltage being delivered, and then controlling and comparing it against what I want, and controlling the fraction of time this switch is on. This is how actually, incidentally, how we also control things like speeds of motors. So when you have a DC motor or some other mechanical device whose speed you want to control, or like the amount of light being, the intensity of light from an LED, or these kind of things, this is a very common approach, that I control the voltage being delivered or energy being delivered to the actuator or device by controlling what fraction of time it is connected to my energy source. So this is the so-called, these are called switching mode power supplies. Main advantage, so we basically, little animation we walk through it. So we alternate between open and closed. Main point is they're extremely efficient. You can get close to 100% or kind of in the 90s kind of efficiency. But there are disadvantages also. So if you ever monitor the voltage on the power line of your home, or while your laptop is plugged in, these things are switching mode power supplies, and therefore when we rapidly turn this guy on off, usually at tens of kilohertz, it injects a lot of noise out there, and that can affect performance of more sensitive circuits. So everything kind of comes at a cost, but these are much more efficient. You can make tiny power supplies. They run cool for more energy constrained embedded systems. That's pretty much kind of what you use. So that's the regulator side. Then the other key element is energy storage. There are two reasons we need batteries or energy storage of some form. One is that for mobile devices, I need to be able to operate disconnected. And the other is that oftentimes you may have intermittency of power. So like if you have, let's say, a sensor with a solar panel deployed out there, when sun is not shining, you don't want it to die, so you would have some sort of a energy storage out there. There are many options, and most common one is to use rechargeable batteries, but increasingly so-called supercapacitors, which are capacitors which can store large amount of energy in a small volume, have become very cost-effective and useful. And then there are other approaches also, like mechanical storage of energy and all. All of these technologies have trade-offs. Batteries are very mature. They can store a lot of energy, but they are not as efficient. Capacitors can go up, supercaps or ultracaps. They do not store as much energy, but they can pump out a lot of power. They can be recharged many times. They leak more, so if you charge them up and don't use it, they kind of leak more rapidly than batteries. So they have these complementary characteristics, and again, kind of depending upon the system, you will see one or the other, or perhaps both being used. It's not all that uncommon that there should be a combination of these. So you can have battery-only systems, capacitor-only systems, or systems which have kind of both being used, or none being used. Like I may just connect it to solar panel, and whenever the sun is shining, my system will run, not otherwise. One of the interesting things that has begun to happen through these kind of technologies is that there is a lot of smartness that you can put, particularly by putting these things, you can enable energy harvesting. So you can imagine systems to which I never need to plug them in. So like a phone which will just always be charged up because whenever it can, it will scavenge energy from outside. So a lot of systems which are operating in inhospitable environment and all, you would often see kind of some storage coupled with some sort of a harvesting capability, and they're essentially perpetual systems, or the term which is often used is energy neutral systems. They're just always on. They will never. There are many sources of energy besides being plugged into the grid that can supply energy for these guys. So I mentioned sun, I mentioned wind. Can you think of others? Scavenging energy. Vibration. Huh? Yeah, tides from the ocean. Okay, good one. Yeah. Yeah, it's the same thing as vibration. Yeah, same thing. Okay, what else? Thermal gradient, hot cold difference. So you can exploit that. You can you can get it from organic material. Sort of literally the way human body takes energy out of that. So kind of involving biological processes. One of the very common ones now is, I mentioned earlier, also from radio waves. In fact, some of the groups have shown that they can scavenge enough energy from the TV signals which are already around us, or even Wi-Fi signals. So there's a group at University of Washington, Seattle, which have been showing sensor chips which literally have no batteries, nothing. They purely operate off harvesting with a capacitor to store things in between. Okay, and you never have to recharge them. They can even talk to each other. They can, I mean, basically they can live forever. Okay. So this is a topic I go a lot more in detail in 202B, but a bunch of technologies. Acoustic noise is another one. They're actually also capable. You can make use of nuclear reaction. So some of the there are nuclear batteries, and then there are ways of harvesting energy from alpha particles, which are emitted by radioactive materials, and convert them into electricity. So current battery technologies, there are a whole bunch of them out there. The most common one that you see used in the smartphones use lithium ion, but you will often see nickel metal hydride in embedded systems and even NiCads. Part of the reason is cost, part of the reason is energy density, and part of the difference also is how much power they can supply. So for example, you would still see radio control cars and all oftentimes make use of NiCads because they can pump out of electricity. In some cases, you will see this thing called lithium thionyl chloride being used. This is a non-rechargeable battery, but it can last a long time in very adverse conditions, high temperature, high pressure, these kind of things. And they have a very high energy density. So the column out here shows how much energy you can store per unit mass, and you would see that this guy is kind of way out there. And likewise, how much energy you can store per volume, per unit volume. So this is a non-replaceable, this is a non-rechargeable battery which is used for extreme condition type embedded systems quite a bit. A topic again in 202B I go over, and one of the things which sort of designing embedded system, these embedded systems around these comes up, is that batteries have lots of non-idealities. What I mean by that is a normal concept of a battery or a capacitor is it's like a bucket of energy. I put some energy into it, and then when I need it, I take out of it. Unfortunately, it doesn't work that way. So one thing we talked about, when I put energy in, and if I don't use it, it's leaking meanwhile, right? So when I use it does matter. But other thing which matters is how rapidly I use it. So let's say I put energy into a battery, and if I draw energy at a high rate, I will actually get less energy out of the battery. Okay, and if I draw it at a low rate, namely a low current, then I'll get more energy out of the battery. So battery chemistries have all sort of weird issues. Another one, this is called a relaxation phenomenon. So you often notice like your flashlight dies, you turn it off, and then after a while when you turn it on, it lights up again. So what's happening there? Right? I'm sure you would have seen this thing, right? Battery dies, turn it off, try it after an hour or two, it seems to come back on. So there's a phenomenon in many physical systems called relaxation. Okay, it's basically there's a recovery effect in the chemical system which happens, which is kind of shown out here. battery voltage drop, I stop using it, goes back up, and then again the system apparently runs. So what this suggests is that in embedded systems, one of the way of getting more juice out of the battery could be to put them into sleep periodically so that the battery relaxes and then you again start. So these are kind of nuances of using batteries more more effectively that come up. And when you combine it with things like changing voltage and frequency and all, they can become a very important thing. So for example, if you look at, let's say this is a battery, and what this is showing is that how much capacity of the battery I can get depending upon what is the current. This is in some funky units, so ignore that. But all it is saying is if I am operating at a high current, I get less energy and therefore less lifetime out of the battery. And if I'm charging it at a low rate, I can get more energy out of the battery. Okay, so the remaining energy kind of gets wasted. Okay, now what that means is that I may have a choice between running a processor at a high frequency and a high voltage, taking out a lot of current, but doing more work in a short time, versus running the processor very slowly at a low voltage and at low current, and then operating in this regime. And the question then becomes, which one will let me do more work overall? Can I still meet my timing constraints? All those kind of issues come up. So one thing as a system designer, one ends up facing is how to get optimal use out of the battery. Next thing in a typical embedded system, again, sort of quick brush overview in this slide set for now. Sensing. So needless to say, sensors are a very critical part of most embedded systems, and this is how you interact with the outside world. A robot may have things like sonar, odometer, environmental sensor may have temperature sensing and humidity sensing and these kind of things. There are broadly two kind of sensors that you will find. Sensors which help the system sense its own state, and sensors which help the system operate, sense its surrounding state. So the first one is called proprioceptive sensors, and the next one are called exteroceptive sensors. So an example would be a processor sensing its own temperature. Okay, so that I can decide whether it's getting too hot and do something about it, maybe turn the fan on. A robot measuring its wheel position to see whether there was slippage happening. External sensors is when I'm sensing the state of the physical world around me, and this could be, for example, what's the light level, what's the ambient temperature, is the sun out, is there sound nearby. So these are broadly sort of two categories of sensors. And one thing to bear in mind is sensors is just kind of the raw data. Okay, what you're really interested in is knowing your state and knowing the state of the physical world, and then making some decision based upon that. So for example, let's say passive infrared sensor, which we find in security systems at home. So these are little things that you see out on the wall, and what they do is they look for infrared radiation emitted by our bodies to kind of to measure that, and they are used to detect motion. They're popularly called as motion sensors. So that's the signal the sensor is giving. What we are really interested in knowing is there someone in the home? Is there a burglar coming in, right? So there are difference between sensing modality and the state. State is something you're going to estimate by taking the readings of the sensor or perhaps multiple sensors and combining them together. So sensors do not say, for example, whatever in this case, Mr. Smith sitting on a chair and wearing a black suit. But you may have sensors which are telling you light level, color, and blah, blah, blah. And then you're going to combine all of this to say, is this thing true or not? So sensors give me a physical signal that then we need to process. And usually a very common way of, like the simple ways of, the simplistic sensors where you may simply say, like for example, if I want to know if this room is dark or not, well, I can have a light sensor, come up with a threshold. But these kind of things work only for very simple stuff. More generally, what happens is you take the sensor readings and then you try to come up with some sort of a model, some sort of an algorithm which processes this. And nowadays, the most common way of doing this thing is to use ideas from machine learning. So sensor data comes in, you compute some features over it. What that basically refers to is you take some sensor samples and you compute some statistics over them. Like over a window of sensor samples, I can say what was the average value, what was the highest value. These could be my features of the sensors, and then you train a model over it using machine learning techniques or statistical techniques, and then the output of that would be something about, is this proposition true or false, or what is the confidence I have in this proposition. So that's the whole pipeline, and then using this, then you in turn may control stuff. So for example, it could be how many people are in this room. Maybe have a bunch of sensors, and then based upon that, I came up with an estimate. There are 25 people in this room, and then that could control the airflow into this room. So that would be kind of the overall system. Variety of sensors. So there is no dearth of different kind of sensors. I've listed a whole bunch of them on the right. Some sensors are pretty standard. Some stuff which are much more complicated, like chemical sensing remains kind of sensitive chemical sensing, biomedical sensing. These kind of things are still kind of hard, like with personal health becoming kind of a big factor, being able to measure physiological state of a person in a fashion which is accurate and unobtrusive. So like, for example, let's say you want to see stress level of a person. Okay, are they stressed out or not? Well, it turns out a good marker of stress is heart rate variability. How is your heart rate varying? The way we measure heart rate currently is chest belts. Now, wearing chest belts is fine, but we cannot do it all the time. So people are trying to come up with sensors which can non-invasively, without something sticking to your skin, kind of do it. So there's always kind of new kind of sensing needs, and people kind of developing new kind of sensors and all. But for routine embedded systems, a lot of stuff is just open the catalog, find something. Main thing which comes up when we are looking at sensors is, firstly, are they internal or external? What is the output signal format? Very loosely, you would see sensors being referred to as analog or digital. Analog signals send out some sort of analog waveform, and you need to digitize them. Digital sensors already have some processing inside them. They usually will talk I2C or SPI or something like that, and then give you a digital thing. Amount of processing needed, simple versus complex. Clearly, things like video or image is complex. And on the other hand, a contact switch which tells me whether the door is open or closed is a very simple one. Sometimes the sensors may be subjected to, depending upon what state you are trying to infer, could be simple or complicated. So take the example of passive infrared sensor I said. Commonly it is used to see, is there motion in the space? But then there are also people who have tried to do that. Can I further analyze it and say, is it a person or an animal, so that we can distinguish between dogs in home versus humans, or how many people are there? Okay, so all of these things require additional processing, and so same sensor, you may cover a spectrum of things. And finally, sensors are classified depending upon whether they're passive or active. Passive sensors do not emit any energy. They just observe the signals and then report it and make some decision on it. So light sensor is like that. Active sensors send out energy and then look at the bounce back from that. So a radar is like that, or a camera with a flashlight is like that, or I have another sonar, lidar, these kind of things. So all of these send out some energy, let it interact with the physical world, and look at the reflected signal. Why do you think what are the pros and cons of passive versus active? Okay, active takes more power and send out energy. Okay.
No, like submarines, they don't like using sonar all the time because give away position.
Okay, so that's a disadvantage. So what he's saying is that you don't want to use this, because if you're operating in a secretive environment, then this could reveal your position, and if you are in a battlefield or something, the enemy missile might come at you, right? I mean, that's why they maintain radar silence, for example, or sonar silence. Okay, so so two disadvantages here, and I presume we can also add cost to it. Why do we still do it? So any advantages? Accuracy, yeah, or actually more precisely, I have control over what is happening, right? Because the signal or energy I'm sending out, I can shape it with a desired characteristic so that, and I let it interact with the physical world, and I can then kind of see whether I'm getting the correct signal or not. And the other advantage, related advantage, is that the other party cannot fool me. Right, because I can embed code in my signal, or I can do other things to my signal so that I can make sure that it is my signal which is coming back, and then kind of work off that. So this has its place, this has its place, both of them are needed, and you will see kind of a combination of these things there. There are a lot of, the other thing is there are certain things I can do with this which we still don't know how to do very well passively. So let's take an example. Let's say I want to create a 3D map of this room. Okay, let's say I want to create that. Suggest me approaches. So I want to create I want to create an image of this room where I also have depth information. What would you use? Okay, sonar is one. Sonar is not very accurate. Wavelength is too much. We'll not. LiDAR. So I have a laser thing kind of scanning and doing it. Can I do it with passive sensing? Two cameras, yeah, stereo vision, okay, and all of these things will, so accuracy will matter. Stereo vision is very computationally complicated, but on the other hand, I can get away with passive cameras. The laser rangefinders kind of things, which kind of just rapidly scan very rapidly in a fraction of a second. They can kind of do a raster scan of the whole room, and they give you a very cool kind of depth image, and then together with the camera, you basically can achieve that. So cars. Some of the self-driving cars and all, they are using radars, for example, for kind of doing the scanning of the immediate neighborhood. So all of these sensors have a role to play. Simple sensors are analog sensors. So if you look at your embed, it has accelerometer, it has a touch sensor with where you slide your finger. So the touch sensor where you're sliding your finger, what happens when I touch it? Capacitance changes because our body has a capacitance to the ground, and then it is feeding into a to D converter, analog to digital converter, and then that change in capacitance translates into a change in voltage, which is what is being read, and you kind of see translated into a position. So many sensors. Fundamentally, sensors deep down, all transducers are analog. Okay, and they take a physical signal and they report it as a resistance, capacitance, inductance, or some other electrical property, which you then translate into kind of ones and zeros after digitization. There are sensors which are fundamentally voltage sources, and there are sensors which are fundamentally current sources. But that pretty much kind of covers things. If you look at an image sensor, so image sensor has a whole bunch of capacitors on the image thing. When sort of light falls, it essentially causes each pixel to charge up differently, and then you read out that charge, digitize it, and that's the image that we get. So what these kind of sensors fundamentally require is measuring voltage or measuring current and doing an analog to digital conversion over that. So these are well-known, well-understood kind of things. Still high speed, low power, all those kind of constraints come in, and there is a lot of sort of people who kind of work on it. Main thing, so they are sort of, it's built into our microcontrollers at this stage. You don't worry about it. Main thing is how often you have to sample. Okay, so classically in electrical engineering, sort of we kind of grow up with, and those of you CS, it might be new to you, the so-called Nyquist criterion, which basically says if I have a signal and if I want to reconstruct it, then I should sample it at twice the highest frequency that is present in that signal. So there are a couple of things. So firstly, the goal out here is reconstructing the signal. But oftentimes I don't care about reconstructing the signal. I need to answer something about it, right? I mean, so let's say you can say that whatever I need out of it is some function of the original signal. It's not the reconstructed signal. So that's one part. The other thing is signals have a lot of redundancies and all. So to give you an example, let's say I am measuring light pattern on the floor outside in the science squad. And clearly there are regions where the light is pretty uniform, there are regions where shade is pretty uniform, and it's kind of would be rather wasteful for me to kind of sample it, the entire space, assuming kind of the worst case. So there are a few ideas which have emerged in recent years to optimize the sampling process. Okay, so that you don't sample at the Nyquist frequency, but you can perhaps push it down. So one concept which came from math side of things is the so-called compressive sampling. And the intuition behind it is the following, that is very common. We sample the signal and then we compress the signal, right? And which goes on to show that there was a lot of redundant information in it. So why not, when we are sampling the signal, we only sample what is the essential part. And what another way of saying is that the signal has some characteristics which they call it sparsity, which we can make use of it. So it's an area called compressive sampling, and which has resulted in some very interesting advances in the sense that I can sample much less frequently and still be able to reconstruct the signal. So that's one part. The other one is adaptive sampling. If I know that the signal is not changing much, I can perhaps sample less often. So, and maybe I can even predict things. So let's take as a concrete example. Let's say you are sampling an ECG waveform. Okay. So we all know kind of what the ECG signal looks like, right? I mean, it's kind of a peak, and peak goes below, and kind of some flattish region, and again things. Okay. And let's say I were to tell you, if you're so not, let's imagine there could be two different goals. One is I want to capture the ECG signal to show it to the doctor, and he or she wants to see the entire true ECG waveform. That's a very different goal than, let's say I were to say I want to monitor the heart rate out of this. In case of heart rate, I need to look at the peaks, identify the peaks reliably, and kind of measure these things. So right there, I stands to intuition that I should be able to get away by sampling a lot less if I knew my goal. If my goal was reconstruction versus answering a specific, computing a specific statistics of the signal, I could do things differently. So that's one part. But even let's say look at reconstruction. Clearly, there's kind of an insane degree of periodicity in the signal. Each waveform is not entirely the same, but they're kind of close enough to be the same. So you could make, so that's another way of saying is there's a lot of redundancy in our sampling if I were to keep sampling just according to Nyquist rate. So compressive sampling and adaptive sampling would basically kind of sample a lot less, maybe even an order of magnitude less, and still be able to reconstruct signals. So again, not the place in this course to kind of go into theory behind this, but main point is that simple stuff, just straightforward sampling. But more complicated stuff, you could do smarter stuff out there. Let's take another example. Let's say I have temperature which is changing at some rate, or some signal which is varying. And again, if I were to say reconstruct, you can use Nyquist. But if I were to say give me the average over it, you can do a statistical sampling over it. You don't have to do Nyquist rate sampling. So designing with sensors, that's one part. What rate you are going to sample, what is the strategy for sampling. Another part related to it is how many bits you are going to sample it with. So the fewer the bits you sample, the more noise you are going to have, and that's going to affect your quality of your inference that you are making. So these are a couple of things to keep in mind. They kind of, you have, as one designs these systems, one has to worry about these things. So sensors have noise, sensors have errors. All of these things translate in, and sensors can be attacked, and sensors can be misled. So all of these things fundamentally effectively affect the quality with which you can estimate the state of the system that you are doing. All of at the end of it, all of this kind of feeds into the uncertainty in our state estimation that is happening. There are, you would see that there is a lot of front-end circuits that gets put around sensors to clean these noise and things like that. So let's take the ECG example again. A very common problem with ECG signals, particularly in hospitals and all, is that the electrode gets displaced, or when you are moving, there are additional electrical signals that may happen. Or for example, ECG leads may pick up the 60 hertz signal from the electrical wiring. So by the time the signal hits the ECG machine, it may look pretty bad. And so all sort of measures get taken, some at the circuit level, some at the algorithm level to clean this up. Almost always the case for like almost any sensor you would face this kind of an issue that you have to do some cleaning up around that. If you don't, then you would have a higher error than otherwise. So an example of kind of signal conditioning that could be done, very common is that I may take multiple readings and average them so that I have a more reliable reading. Or I may take the median of the readings so that I can get rid of the outliers. So I can take a window of samples and then take the middle reading out of that. Mechanical sensors often have issues that they jostle or vibrate, so they inject additional noise as well. So again, very sensor specific. If let's pick some other sensor. Let's say images. What kind of impairments do you think are going to be there? I have a camera capturing an image. What's the source of noise? Or what are possible sources of errors and noises? Okay, camera resolution is one. That limits what I can, so number of pixels is one. Okay. Lighting can affect things. Occluding objects. Okay, well, kind of related to lighting. Okay, what else? Huh? Rapid movement, yes, because of my frame rate, I mean, that can affect things, absolutely. What else? Failing pixels. Okay, yeah, pixels can fail, sure. Noise in the power supply. What about noise in the sensor itself? No one said that. These are capacitors, they're being charged up, right? I mean, there's always going to be noise. In cameras, what happens when you are operating at high ISO levels, you have a noisy image. When you're operating at a low ISO level, it's a very clean image. I don't know anyone of you to photography, right? I mean, the more sensitive the sensor, basically you have amplifiers operating at a high gain, and so they magnify the noise also, which is why when your camera is operating in dark light, you have a grainy image, and when it's operating in good light, you have a good sharp image, right? I mean, because the sensor is in a different regime. So every sensor has these issues, and you have to kind of design a combination of some measure at the hardware side, but usually at the algorithm side. Sensors need to be calibrated. So what that refers to is that, remember, sensor is taking a physical property and converting it into an electrical value, and then we digitize it and then get a number. For the moment, let's assume that the final step, taking voltage or current and digitizing it, is well done. But the first step, physical property to a specific voltage value, that depends upon the, how good the sensor is, and two multiple sensors from the same manufacturer made at the same time may behave differently. Like, for example, you buy two weighing scales from the same manufacturer, stand on one, stand on the other, you'll have different errors, right? I mean, so sensors need to be calibrated. You need to take, for that specific sensor, you have to map the physical value into the corresponding electrical value, or kind of the eventual number that you get out of that. So reasons are many: manufacturing error problems, environmental condition, aging. Sensors change over time, because maybe in a weighing scale it could be the spring tension changes over time. In a chemical sensor, the concentration changes over time. All those kind of things can happen. So calibrating a sensor basically means that finding some of the crucial parameters of a sensor which will help you get a more accurate value. Temperature sensors, all of these things need to be done. And the way you kind of do it is by two broad approaches. One is I take a known input and see what my sensor is reporting, and I do it at a few different values, and then form a calibration function of some form. So known input, check my reading, correct against that. And the other one is I have a reference sensor, I have a costly sensor, and I compare the two readings, and I basically assume that this expensive sensor is telling me the reality, and I calibrate against it. So this reality is called the ground truth. okay? Or another term in medical science they often use for it called the gold standard, okay? So I'm measuring something and I would say, what is the gold standard saying? Gold standard meaning a high quality sensor or the best known sensor, and kind of a new sensor I have. So let's say, for example, I suddenly come up with a new sensor to come up with heart rate variability. And then I have a high quality ECG machine. I'm going to compare against the two and kind of do it. So knowing the ground truth, at least for some initial phase of your system, or occasionally it does matter, partly for collaboration, partly also for training things, in the sense that when I take the sensor data and develop algorithms to then infer something about it, like whether I am stressed or not, or whether there's a cardiac event happening or not, then knowing the reality so that I can train the algorithm becomes important. So calibration depends in turn on a known input or a known good sensor, and then all of this kind of helps you design a more robust system. So we saw that to deal with these issues, you have to calibrate sensors, you have to take care of noise and all. And the final part, which we often do, is sensor fusion, where which basically says instead of depending upon only one sensor, you now begin to combine readings from multiple sensors. One reason you do it is to make things more robust, and the other reason is oftentimes one sensor may not have the complete view. So let's say I want to know what's happening outside on the Bolter Hall, outside in the quad. A single camera may not cover things. So I may have multiple cameras whose overlapping images I may have to stitch together. Or for example, go to the problem of intruder at home, burglar at home. Motion sensor gives me part of the information, but we realize that it can be fooled. So we may combine it with information from, let's say, door and window sensors, and the two together can give me a more reliable estimate of what is happening. So sensor fusion is kind of the final part of the story, where we basically take readings from different sensors, which may even be located farther away, and kind of combine them to reach my inference. All of this costs stuff, okay? You need to process it. And one of the things which a lot of the sensory systems face is, where should you do this processing, and ideally, and what sensors you should pick to minimize that processing. So let me kind of rephrase this thing. In our tiered architecture that I've shown in the previous slide said, I had the devices, I had the gateways, I had the cloud. And you could imagine that I could take the raw sensor data and just send it to the cloud and have everything be processed out there. Not sustainable from cost and power perspective. On the other hand, the other extreme, I could say, let's just do everything on the device. That's also not doable because I'm resource constrained out there. And moreover, I may want to combine information from multiple devices, okay, multiple sensors. So that may not be possible either. Maybe stuff can happen at the gateway. So all of this kind of boils down into this communication, computing trade-off, picking the right type of sensor. If I can get away with a cheaper sensor, then I shouldn't have to do. Cameras are a great universal sensor, but they are an overkill in many cases, and they require too much bandwidth and too much processing. On the other hand, there are certain things only cameras can do. So like, for example, if I wish to count excuse me, how many people are in this room at any given time? Well, certainly cameras can do it. I can kind of put cameras and do some fancy image processing and all, but perhaps you can do it through a simpler sensor as well. Like, for example, maybe I can count how many times the door was open and closed, and whether the person was coming in or out. Maybe I can look at other signals like a lot of you have phones and devices. Maybe I can do some Bluetooth signal snooping and use that data. Okay, and all of this can fuse and result in an estimate. Or I can have cameras everywhere and work off that. So designing kind of the right type of sensing becomes important. Okay, I think I have made most of the points. Yeah. Let's take another one, measuring distance to an object. I can do it through ultrasound, time of flight, I can do infrared, I can do two cameras with a stereo, I can do a single camera with some assumptions about environmental structure, I can do a laser, I can do laser plus camera and many others. Okay, and so I guess the main point I want to leave you out here is that uh, there are two parts of it: selecting the right type of sensors, and but oftentimes you don't have that choice. You are given a set of sensors and you're asked to do some sampling. Then it boils down to where should you partition the computing? Should it happen at the sensor device? Should it happen somewhere in the middle? Should it happen in the cloud? Where should what happen? Some processing can only be done on big cloud side. Some processing can be done on the device side. Communication is costly. All these balancing all of these things out kind of becomes is kind of a challenging part out there. Next up, actuation. So many embedded systems are purely sensing, but also many embedded systems now do various kind of actuation. That is, they may have some device which affects the state of the physical world. And it could be any number of things. It could be light, wheels, grippers, gun, water hose, all sort of things. Okay, I mean these are all examples of actuators. They do something to change the physical state of the world. Uh, no motion here, turn the light off. That's an example of a feedback loop. I'm sensing light, the action is turning off the light. I'm sensing motion and turning off the light. So essentially in these systems, there's a feedback loop, sensor is being processed, and then a command is being given. And again, the same question of where the action happens come into play. In some cases, the decision takes place all the way in the cloud. In some cases, it can happen within the device. And it really boils down to how agile it needs to be and how lightweight it is computationally. Robots are a great example of a lot of things have to happen locally, because if imagine like you are doing robot is manipulating some fragile object, so it's using a force sensor to then control the amount of pressure it is applying on the egg versus a metal piece, for example. That is not something you are likely to close from long distance. On the other hand, if it's a medical system where uh, based upon my daily activity, it is going to control my drug level for the daily drug level. This is something clearly may require more medical knowledge and might go back to the cloud. So there are sort of control loops happening at different tiers. Actuator, so there are two terms that you would see. Effector is the device through which the effect happens, injection, gripper, things like that. And actuator is the mechanism, kind of the motors or other form of things that sit behind the actuator to cause them to have the action. Mechanical actuators are perhaps the most commonly one which we normally associate with the actuators. It's a more general concept out there. You have motors, hydraulics, pneumatics, photoreactive material, all chemical stuff, changing chemical concentration. So chemically reactive material, thermally reactive material, piezoelectric materials like vibrations and all, and there are many others. There is kind of a whole bunch of these things out there. Again, I guess the main thing I would say at this stage is that they are pretty diverse, and it's very hard to kind of have a common thing across them. One thing you would see is that many processors have a set of two types of signals which target actuators. One type of signal is D2A converters. Okay, so they basically let you take a digital value and generate a voltage. So you can create a waveform which you can then feed into some electrical circuit and combine out. The other one is called pulse width modulation, or your embeds have it. They let you generate waveforms with right duty cycles, okay, and they are used oftentimes for motors and a lot of these other actuators. So you'll find that platforms like Embed or Raspberry Pi and all, they usually have support for these kind of actuator control signals also. One thing is that controlling actuator tends to be pretty timing sensitive. So what you would also find is that they usually are, so things like PWM, usually they have hardware support for it. So you can tell the hardware unit, I need a PWM waveform with this timing characteristic, and it takes care of it. Because otherwise, doing it in software yourself all the time can be pretty expensive to do it. Okay, so as you do some of the homeworks where I ask you to generate waveforms and all, one thing you would notice is doing a little bit of study of the processor itself to see if you can use its timing or counters or PWM hardware to generate these things will result in a lot more efficient and better solution than trying to do these things in uh, replicate these things in software yourself. They will be less accurate that way. So making appropriate use of these hardware capabilities become quite important when you are generating signals. And likewise, when you are sampling things, like for example, if you have to sample a signal every 1 millisecond, then counting milliseconds within your program versus kind of setting a timer to generate a 1 millisecond interrupt and then doing things on it, the latter would be a lot better. I'm going to skip these slides and let's continue this thing next time. So we'll go into software. That will be the next part.